All right, so this is going to be the video for infinite limits and limits at infinity. So just to start off, we have an example of f of x equals 1 over x minus 1. This function is interesting because it has a vertical asymptote at x equals 1. This vertical asymptote can be figured out if you take the function and break it up into the numerator and the denominator as two separate functions and solve for the denominator equal to 0. So we would take that x minus 1, set it equal to 0, and then solve for what the x values would be that would satisfy that equation. We can also take a look at what happens as we approach that vertical asymptote. So say that we took values that are slightly larger than 1, or we looked at the right-hand limit. Those values would approach a positive or a very large positive number. And as large of a number as we wanted to get, we could find an x value which is close enough to 1 to reach that value for the function. So any positive valued number we can reach by choosing an x such that it's close enough to 1 to be that high when we do f of that number. Same thing, but with negative values, and from taking x values which are slightly less than 1. So if we were going to look at very large negative numbers, then we could potentially find an x value which is close enough to 1 such that the f of that number would give us as large of a negative number as we wanted. And so those limits go off to infinity because of these properties. The one from the right-hand side goes to positive infinity. The one from the left-hand side goes to negative infinity. But this is a property of vertical asymptotes where the values of the function go off to infinity as they approach them. So if you're noticing that happening with a function that you're working with, then you have a vertical asymptote on your hands. All right, so we've already talked about how to find the vertical asymptotes by setting the denominator equal to 0 and solving. And we've discussed a little bit about what the vertical asymptotes are and what happens near them. So I think we're pretty good to move on now. We can also talk a little bit about what happens at infinity for certain functions. So let's say that we had some constant over a power function, or x to some p. Then if we take x going to either in positive or negative infinity, then the value of that function will approach 0. That's because if you take any particularly large number and plug it into the denominator to any certain power that you wanted, you will get a relatively small number overall. And for whatever number you wanted to approach for 0, you could find an x value to reach that point for any function of this form. And it wouldn't matter if you're going to positive or negative, that would still apply. All right, so if we're doing the limit of x going to positive or negative infinity for a different function, such as k, which is a constant, times the power function x to some p for any power, then that will go to positive or negative infinity. And this one is sort of similar to the concept for the vertical asymptotes. The x to the p power will approach whatever, or will surpass whatever value you wanted if you choose a large enough x in either direction, either the positive or the negative direction. And so if you're looking for a particular size of value for the output, you can find that initial input to reach that. All right, and if we wanted to do polynomial functions, they have a very similar property where if you're doing the limit as x goes to positive or negative infinity for a polynomial function, that will also approach either positive or negative infinity, depending on what the polynomial function is. Those are some kind of interesting properties of limits as you're taking the value of x going to infinity or negative infinity. We can also talk about how to analyze rational functions in terms of their positive or negative infinite limits or limits at infinity. So if we have a rational function, it'll be of the form of a polynomial in the numerator and a polynomial in the denominator. This will mean that we have a leading power term with the highest exponent as that particular part of the function. And that'll have a predefined exponent for the numerator. We can call that the a sub m x to the mth power term. And then for the denominator, we can call the highest order term the b sub n x to the nth term. And that one will, those two terms, the one that's the largest in the numerator and the one that's the largest in the denominator, will be what the limit can be reduced down to for that rational function. So instead of saying limit of x going to plus or minus infinity of rational function r of x, we can just say limit of x going to positive or negative infinity of a sub m x to the m over b sub n x to the n. And that's a simplification that we can make, which happens mainly because the leading term in a polynomial will eventually outweigh all the other terms just because the exponent is has so much power with the higher order. All right, with this particular reduction, we have a couple of different situations that we can run into. We can have if m is less than n, then the limit as x approaches positive or negative infinity of the rational function equals 0. If m is greater than or is equal to n, then we can say that the limit as x goes to positive or negative infinity of r of x equals a sub m over b sub n. And then finally, we can say that if m is greater than n, then the limit as x goes to positive or negative infinity of our rational function is equal to either positive or negative infinity. And this one really depends on what a sub m, b sub n, and our m and n values themselves are. That one will be determined by the specifics of the problem, but the other two are pretty specific as to what they come out as. So, all right. I think that's it for this one, and I'll see you guys later.